Hi guys, welcome to another A2 mechanics paper. So our first question is one of these projection questions. We have a particle being projected from the ground at some angle, like so, and it's got some velocity v, some resultant velocity. And the angle it's being projected at is given as 30 degrees. So we know that we can resolve this velocity, like any vector, into, v sine of 30 and v cosine of 30. Now, we're told later that at some point the particle is at an angle of 15 degrees above the horizontal. So what they mean is it's a different idea of the angle of the velocity at the beginning. So after 2 seconds, this is in velocity space. This is going to be now in position space. So if we drew a line from O to the place where it is P, the particle will have traveled, in some parabolic arc, like so. And at this point, the angle that it's making is 15 degrees. So like if you drew this line from O to P, this straight line, like so, you would get that this angle would be 15 degrees. So how do we solve this question? Well, I think the best thing to do is to realize that if you have, some particle like here, like this, and this is the delta x that it's traveled, and this is the delta y, you can recognize that the tangent of the angle, which here is the tangent of 15 degrees, is equal to opposite over adjacent, which is delta y on delta x. And now we just need expressions for delta y and delta x. Well, y, we know that the only force acting on this thing is gravity. So that's the only acceleration it'll feel. So delta y, the change in y position, the y distance that it's traveled, is the initial velocity, v sine of 30, times the time that's passed, minus 1/2 x gt squared. And delta x, well, there's no acceleration in the x direction, so it's just going to be the initial velocity in the x direction, which is v cosine of 30 degrees, times time. So that means that the tan of 15 must be equal to, we can divide them by each other and we can cancel a factor of t, will be v sine 30 minus 1/2 gt over v cosine 30. And you can see that we can solve this. We know what tan of 15 is. We just put that in the calculator. Make sure that you've got it on degrees and not radians. We know what the sine of 30 is. We know what g is. We know what t is. That's 2 seconds, they've told us. We know what cosine of 30 is, so we can rearrange this whole thing for v. So we'll get that v is equal to minus 1/2 gt over cosine 30 tan, cosine 30 tan 15 minus sine of 30, which, if you put it all in, is 37.3. Okay, question 2. So we've got this cone held in place by this force. And so this is all going to be about the center of mass. So we know from the formula booklet that the center of mass of a cone lies sort of 1/3 up the way from the base, or equivalently 2/3 from the vertex down the center line. So it's over here. And what we want is moments around P. So its equilibrium is being maintained. So we know that the moments must balance. So what forces do we have acting? Well, we have the force of gravity acting. Let's do a nice straight line. Can I do that? Is that a... Here we go. It's a nice straight line downwards. So that's the force of gravity. And we have the force F. So we know that these moments must balance. So what is the moment? So we'll take moments about P. And the moment associated with F, remember that a moment is just the magnitude of the force multiplied by the distance between the point about which we're taking the moment, which is here in this case is P, and the line of action of the force. So the line of action of the force here is this sort of vertex here. So really, the distance between P, like the shortest distance, the perpendicular distance between P and that line of action, is the radius of the cone. Yeah. So that's a right angle. And so it's pretty easy to see that if this angle is 30, this angle is also 30. And that one at the bottom is 60. So this this side here, R, is equal to 0.8 times the tangent of 30 degrees. So the moment by F must be F times 0.8 tan of 30, which, if you put in your calculator, is 4 square root 3 on 15 F. So I'm just, setting up the problem here, which I think will all come through. For this first part, so let me actually drag and drop this. I'll copy and paste up here for future reference. And let's look at this first question. So they want to know about the weight of the cone. So what we need to know is to look at this triangle here, this sort of big one, including the 30 degrees on the left-hand side, and realize that this distance here is the same as this distance here. So you can see this is a right angle triangle, and this distance is going to be 0.8 sine of 30 degrees. So we have that the moment of the weight must be equal to mg times this distance here, because this red thing is the line of action of the weight, and we're looking. Sorry, these distances are not the same. I misspoke before. We're looking for this distance here. We have this full distance, and we know that this point is 1/3 up here. So these are similar triangles. So this is going to be, this distance here is going to be 1/3 of the full 0.8 sine 30 distance. So maybe to make it a bit clearer, I'll say, let's do it in orange. Here we go. So this full thing is 0.8 sine of 30. And then this piece here is 2/3 of it. And that's the same as this piece here. So this is going to be yeah. Actually, I've got that it's 3/4, but I'm pretty sure it's 2/3. Let's say 2/3 sine of 30, 0.8. For some reason, I've written down 3/4. It might actually be 3/4, but let's say 2/3. And so the moment is going to be mg times, I believe, 2/3 sine of 30 times 0.8. And if we put that in the calculator, let's see if I got that right. It's got a weight of 20 newtons. That's mg times sine of 30 in degrees times 0.8 times 2/3. No, that's not right. It should be 3/4. Sorry, I miswrote that. Bit of confusion. This is actually 3/4, and this is 3/4 here. So a quarter. This is a quarter of the distance to that. And if you plug this into your calculator, you will get 6 Newton meters. Okay, hence find F. Well, we go back to what we had before. So we realize that these moments must balance. So this thing must be equal to that. So this is going to be equal to 4 square root 3 on 15 F. And you can solve this for F. Okay, question 3. So here we have here's a picture of the setup. So we have some ceiling with a point O, and there's a elastic string hanging to particle P. And what forces do we have? Well, we have the weight of P, of course, mg, and we also have the tension in the string, T. So firstly, we know that we're being asked to deal with the energies. So the initial setup is this one, and we can do comparison using conservation of energy. So let's think about what energies are involved here compared to what energies are involved in scenario 2, where you've got this thing hanging, but it's sort of on its way up. And there's going to be no tension in the string because there's no elastic. So there's just mg acting downwards. Okay, so what happens? What energies are involved when we give this thing a kick? So just as it starts to move. Well, we have the elastic energy in the string. Now that's going to depend on the tension. So using the formula booklet, tension is lambda x over L. And we know that just before the thing is given a kick, where it's hanging in equilibrium, this is equal to mg. So therefore we can solve that. This gives us that x, so the amount that the string is distorted, that it's been stretched, x is equal to lmg on lambda. We have, all of these quantities. We have L, we have M, we have G, we have lambda. And we know that therefore the energy stored in the elastic potential energy stored in the string is, from the formula booklet again, lambda x squared over 2L, which we have. We have all of these things. We worked out what x was, and we have the others. And we know that we've given it this kick of kinetic energy. And this is 1/2 mv squared, and we have all of these quantities as well. We have m, that we're told that v is 1.8. So these are the things that we add. Now there is no gravitational potential energy at this point, because it's basically, we can just say that this is 0 height. And we're just looking at changes in potential energy. So all we care is about how far it's gone up now. So how far has it gone up? Well, we're told that let's do it one by one. So potential energy stored in the string, elastic potential energy, is 0 in the second scenario because the string is slack, like it's exact, x is equal to L. It's exactly its energy, sorry, it's exactly its natural length. And we know that the kinetic energy is 1/2 mv prime squared. So the v prime is what we're looking for. But we also know now there's this potential energy gravitational, which is m times g times h, the amount that it's gone up. And we know that originally it was the length of the string was the natural length plus x, and now it's just the natural length. So the amount that it's gone up is our original x. So you just add these together, set them equal to that, and that will give you v prime, which is what you want. Okay, question 4. This is a shape that does crop up a lot in these past papers, this kind of rectangular plus triangle prism. It's a uniform solid prism. So one of the things we can remember about that is that if we have to talk about the mass of the prism, we can equivalently just use the area, right? Because the whole thing is, it's uniform. So, and maybe it looks like this in full 3D. So really a mass is a density, rho, times a volume. But because we'll be setting things equal to each other that have, the densities and on both sides and the sort of depths as well. So volume is area times depth. We basically will be effectively dividing through by them. So I'm just going to look at the areas. Those are the important things. So we have that the area of the rectangle, well, that's just going to be 1.6 times 0.4. That gives us 0.64. And the area of the triangle, 1/2 times 0.4 times 1.8 is 0.36. So that means that the total area is equal to 1. Now, the equation that we need to remember for these kinds of questions is that, m total times, what should I use? Some vector, v is a bad idea. Let's just use a big X. Total with an underline means this is a vector, is equal to m1 x1 plus m2 x2 plus, basically, if you have a bunch of objects, object 1, object 2, object 3, and you want to find the position of the center of mass, you just need the individual masses and their centers of mass. So we want this composite object, and so we're going to work out where the center of mass is individually. Well, we know the center of mass of a rectangle. That's pretty easy. That's just going to be right in the middle. And so X rectangle is going to be halfway along here. So I'm going to call this 0. This is my 0 point where A is. So that's going to be 0.2 and then up 0.8. Well, that's pretty easy. Now, the triangle is a little more difficult, and I think the best way, apart from memorizing, formulas, is to think of it in terms of vectors. So I'm going to just drop some lines here. And you remember, so it's in the formula booklet. So the center of mass of a triangle is the sort of meeting point of the lines. It's called the centroid of the circle. So if you draw a line from the midpoint of each side to the opposite vertex, where all these 3 lines meet, that's where the center of mass is. So the best way I found to do this is to pick one of the midpoints. I'm going to call that M. And this is, of course, X triangle. And think of it in terms of vectors. And this is a point, the point D. So what are the coordinates of the point M? Well, you go along 0.4 in the X direction. And then you go up like the full 1.6 and then down 0.2. So that's 1.4. What about D? Well, to get to D, you need to go over 0.4 and then another 1.8. So that's 2.2. And you need to go up 1.6. So now how do I get to X triangle? Well, if I'm thinking just in terms of vectors, just giving someone directions using these M and D vectors, I know I can get there by going to M first and then going 1/3 of the way. So this is the fact about triangles, is that this vertex is 1/3 of the way along this line from M to D. And it's also 1/3 of the way of the line from this midpoint to that midpoint, and 1/3 of the way from this midpoint to that vertex, and so on. So X, a triangle, I can get there by first going to M, and then going 1/3 of the way along the line from M to D, which is just the vector D minus M. So you can see that this is going to be equal to 2/3 M plus 1/3 D. And if you work this out, this gives you basically an X value of 1 and some Y value, which we don't actually need. So we're looking, because they're asking us for the distance from the center of mass of the prism to the line AB, which is this vertical line here, you only really care about the X direction. So the total mass is 1. And I'm multiplying it by this, this vector that I want, X total. And let's just look at the X coordinate. And that's going to be equal to the mass of the rectangle, 0.64, times the X coordinate of the center of mass of the rectangle, which we worked out before was 0.2, plus the mass of the triangle, 0.36, times 1, which was the distance, the X coordinate of the center of mass of the triangle. So if you work all this out, you'll get that it's equal to 0.488. Okay, so now they want us to find the least and most possible values of t. What they mean is that the whole thing is not going to move, like it's held in equilibrium. So there's two possibilities. Either the thing could, it's in limiting equilibrium. So in order for it not to move, there has to be a zero moment about any particular point. So this T, if it's really, really strong, then the thing could be about to topple around A, toppling that way. Or if it's very, very weak, the thing could be about to topple that way around F. And it's not doing either of these things, so both of these things must be equal to 0. So if this is, so A gives you T max. So if it's very, very strong, that's the one that we care about. And this is going to give you T min. And so the T max and T min will tell you the maximum possible, the minimum possible that you could have TB without it doing one of these things. So moments, so for T max, moments about A, you get that, so the moment of T about A is just the value of T multiplied by the distance between the line of action of the force, which is this top horizontal line, and A, so that's just the height, 1.6 meters. So that's T max times 1.6, and that must be equal to the weight times the distance to the weight, the line of action of the weight. And the weight just acts vertically, right? So the line of action goes down like this. So you just care about this distance here. It's not the distance from A to the center of mass. It's the distance from A to the line of action of the weight. And that's what we worked out, right? So that's equal to mg times 0.488. And mg, we're told, is 100. And you can solve this gives that T max is 30.5 newtons. Okay, so T min, it's the same business, except we're going about F now. So T min, and again, the distance from between F and the line of action of T, which is, again, this horizontal line, it's still 1.6. But now the weight is at a different distance. So this distance is 0.4. So in fact, I completely drew this wrong. It should be over here. Oops. So this distance is 0.4, and the distance from A to the center of mass is 0.488. So it's actually a little bit below, beyond. So the distance between F and the line of action of the weight is just 0.088. So this is going to be equal to 100 times 0.488 minus 0.4. And you see that this gives T min is 5.5 newtons. So much, much less. Okay, question 5. So we're given the equation for the trajectory of this ball. And you see we're given it parametrically, by which, non-parametrically. So we're given y and x, but it doesn't say anything about t. So although they don't really state it in this question, the assumption is that the only acceleration that the thing is undergoing is due to gravity. Like, you need that information. So firstly, let's show that B is projected horizontally. And for this, we're looking at the velocity, when it's initially projected, like so. So this theta, we're going to use this fact again, that the tan of theta is equal to Vy over Vx. And so this is going to be equal to, so Vy is just dy dt, right? So this is dy dt over dx dt. And this is equal, if you go 1 over a derivative, you can just flip the direction of the derivative. This is dy dt times dt dx. And this is just a chain rule version of dy dx. And if you differentiate that, you get that this is minus 0.1 x. Well, therefore, the tan of theta when x is equal to 0, so at the beginning, is 0. And this means that theta is equal to 0. So this means that v is equal to vx, or it's projected horizontally. Okay. Now, they want us to look at some later stage, and they want us to tell them the value of y when the situation is like this. So when that's 60 degrees, and this is v at some later time, and so this is going to be vy, and this is vx. So we use again the tan thing. We know the tan. Oh wait, sorry, I forgot a piece. So this you showed that it's projected horizontally, and they also want us to find that its speed of projection. So for this, we know that the only acceleration is due to gravity. So let's compare our usual constant acceleration equations, and gravity is a constant acceleration, so we can use them, to this equation for y. So we know that minus 0.05 x squared, so this is a distance traveled by y after some stage, is equal to initial y position, which is 0, minus 1/2 g t squared. So if you rearrange this, you will get that x is equal to the square root of g over 0.1 times t. And therefore, if you differentiate, you get that dx dt is equal to square root of g over 0.1, which is 10 meters per second. Okay, so now they want us to to look at some later stage. So again, we use this tan business. So we have a tan of 60 degrees, where it's opposite over adjacent, right? Vy over vx, which again is dy dx, evaluated at this x prime. And therefore, this must be equal to minus 0.1 x prime. You know, that's dy dx is minus 0.1 x, and we're evaluating at some x prime, so it's minus 0.1 x prime. And that is equal to tan of 60. So this means that x prime is equal to 10 times the tan of 60 degrees, which is 10 square root 3. So therefore, we can just plug this back into the equation for y. Y prime is equal to minus 0.05 times 100 times tan squared of 60 degrees, which is just x prime squared. So this is equal to minus 15 meters. Now, we have that Vx, well, this is not changed. This is the same as Vx at t is equal to 0, right? Which we worked out before was 10 meters per second. But we know this is equal to v prime, this new velocity that it has right now, which might be changing in direction, times the cosine of 60 degrees. So the velocity, the resultant velocity has now changed, but the x velocity hasn't. So it's been accelerated in the y direction. And we know that this is the relationship between the x velocity and the new velocity. So if you solve, you get that v prime is 20 meters per second. Okay, question 6. We have the straight line with OA and B on it. So there's O, there's A, and there's B, just to give you some visualization. And we have a particle traveling along it. So this is a differential equation question. And usually, as usual with these things, you should know that Newton's second law and then what that looks like with derivatives. So we have F is equal to ma, and acceleration is just dv dt. And we know, we're told that the force, it looks like that. So this is 0.4 v to the 1/2. But if you look at the question, we're looking for a relationship between v and x. So we're going to use chain rule. So this is going to be dv dx times dx dt. And you realize that dx dt is just v. So this is mv dv dx. So these two things are equal. So all I do is I transfer I divide this side by that one's 1/2, and I get that mv to the 1/2 dv dx is equal to 0.4, and then you divide both sides by m and multiply by 3, and you will get, so m is 0.6. Divide both sides by 0.2. Yeah, divide both sides by 0.05 or something, and you will get that. You'll get this relationship. 0.6 will turn into a 3, and the 0.4 will turn into a 2. You know what I'm saying? Okay, so now you need to express v in terms of x. Well, this involves integrating the equation that we had before. So we have 3 v to the 1/2 dv is equal to 2 dx, separation of variables. You integrate both sides. We need our boundary conditions now. So if we look at the question above, you see that when x is equal to 1, v is equal to 1. So the lower, remember, the boundary conditions have to match on both sides, and then you'll get the right answer. So 1 and 1. You can also do it by solving to an indefinite integral using a constant c and then insert the things manually. That's also fine. And we're integrating some later time where x is just equal to x and v is equal to v of x. And if we integrate this, we get that this is equal to v to the 1. Oh. Here we go. So integrated. So the v to the 1/2 becomes v to the 3/2, and that means you have to divide by 3/2, like multiplying by 2/3. This is still the 3 out front. And you're evaluating between 1 and v, and this is equal to 2x between 1 and x. So you get that 2v to the 3/2 minus 2 is equal to 2x minus 2. And so v is equal to, and then you raise both sides to the 2/3 power, x to the 2/3. Okay, so now they've given us this fact that AB is equal to 7. So once you get from A, if you start at A and then go to B, that distance is 7 meters. And now they want us to find the value of t. So we're going to have to re-express this using t. So we have that the velocity, v, well, that's just dx dt. And we also have from up here that this is equal to x to the 2/3. So we have a relationship between x and t. So we have x to the minus 2/3 dx is equal to dt. And let's integrate this. Integrate this between, so if you look back at the question, you see that it's initially at A, and when it's at A, the value of x is 1 meter. So A is 1 meter away from O. But we're measuring time from some initial time. So when time is equal to 0, x is equal to 1 because it starts at A, not at O. And at some later time, it is time t seconds, and the value of x is, when it passes B is 7. So if we integrate this, we have x to the 1/3 times 3. So this thing, you just add 1 and then divide by the appropriate thing. So divide by 1/3 between 1 and 7 is equal to t between 0 and t. And this will give you that t is equal to 3 seconds. Excuse me. Okay, final question. So we have an elastic string again. So we know we're going to be needing to deal with these equations. Those sorts of equations. So initially, we have the situation. And let me just mark out that this length here, this long bit at the bottom is going to be 0.4 divided by cosine of theta. And so the first question is asking us to find the tension in the string. So what do we know? We know lambda. Well, what is x? Well, x is just going to be the natural length L. Sorry, no, it's going to be the actual length, big L, minus the natural length. So that x is saying how far has the thing been stretched or shrunk from its natural length. So the big length, well, that's going to be equal to this vertical length plus this slanted length. So that's 2 plus 0.4 over cosine theta. Minus the natural length, which we're told is 2 meters. So x is just 0.4 over cosine theta. So therefore the tension, which is lambda x over L, is lambda, which is 15, the modulus of elasticity, times 0.4 over cosine of theta divided by L. And this is equal to 3 over cosine of theta. Now you know, so the second part of the question, you know that this thing is not moving up and down. It's moving in a circle, but it's not being pulled down to the ground and it's not rising up into the air. So we know that its weight is mg, and therefore this component of the tension, which is t cosine of theta, must be equal. So we have that mg is equal to t cosine theta. We plug in our value of t. That's t cosine theta times 3 over cosine theta, so that's equal to 3. So the mass is equal to 3 on g, which is 0.3 kilograms. Now they want us to show that the value of omega, you know, the rotational velocity, does not depend on theta. Well, for this, we use the other component of the tension, which is t sine theta. And that is equal to the mass times the rotational acceleration, which is mv squared over r, or equivalently mr omega squared, because we know that v is equal to r omega. Now r is equal to 0.4 over cosine of theta times sine of theta. So if you look back up the diagram, you see that the hypotenuse of this thing is 0.4 over cosine theta. We got that at the beginning. Therefore, this radius is the hypotenuse, 0.4 over cosine theta, times the sine of theta. So we now plug this in, and we plug in the value for t. So it's t, which is 0.4 over cosine of theta times sine of theta, is equal to m times r, which is 0.4 over cosine of theta times sine of theta, times omega squared. And sorry, not 0.4. This is 3. Sorry, this was our tension. 3 over cosine theta times sine of theta, so that's the t sine of theta, is equal to all this business. And you see that the sine of theta's cancel and the cosine of theta's cancel. So you get that omega is equal to square root of 3 over m. Right, no, there's the 0.4, so that actually becomes square root of 15 over 2m. So omega is equal to 5 if you plug all that in. Now they're asking us to look at the potential energy. So the potential energy stored in the elastic, as the formula booklet says, is 1/2 lambda x squared over L. And this is equal to twice the kinetic energy. And if we plug in V is equal to R omega, this is the same thing as, let's cross out those 2's. This is the same thing as mr squared omega squared, which is 25 mr squared, where this x is the same as we got before, 0.4 over cosine of theta, and this r is 0.4 sine theta over cosine theta. So you see that the 0.4 on this side will cancel. So remember that they're both squared. So the 0.4 squared will cancel with the 0.4 squared, and the cosine theta squared will cancel with cosine theta squared. So all that'll be left is on the right-hand side, there'll be a sine squared theta. So this is 1/2 lambda over L is equal to 25 m sine squared theta. And this gives you that the sine of theta is equal to 1/2, because we know lambda, we know L, and therefore that theta is equal to 45 degrees. And that's all there is to it. I hope that was clear. Please let me know if you have any questions on the group. One of us will try and answer them. And see you next time. Bye.